way. And actually, it's the kind of textbook problem that I think probably should be in the future part of the notes, because it really was a good intro to what we were covering today. And I think sometimes my best teaching strategies come by complete accident. So that worked out nicely, because now we're looking at something that's much more elaborate, but we'll be able to navigate it a little bit easier because we have a little bit of experience. But let's talk a little vocabulary. Contingency table is also known as a two-way table. All right. I think both kind of, sort of get at what's really at root, because a contingency table, contingency plans, really implies the idea of conditions. All right, if this, then that, But two-way is really getting at the physical attributes of it. All right, so two-way table contains two variables. So two-way tables really are just an organizational strategy for multiplication rule type situations. And it doesn't necessarily have to be multiplication. It could be addition rule, but having an organized way of looking at things is probably the easiest pathway to success when it comes to probability. All right, so having it in tabular form is a good thing. All right, now the statement here, this is the probability of one event occurring given that the other has already occurred. All right, so that's a conditional probability. All right, so conditional that's weird. That should say that there. Either I deleted it, or this is the first time after about, like I said, 20 years that I've noticed that it's not there. Conditional probabilities is what is the probability of one event occurring given that another has already occurred, not contingency. Contingency table is just an organizational strategy for data, right? I just said it in the past, I don't know. Yes. All right, so the statement here, the above formula is derived from the general multiplication rule. So if you go back to the previous page, we had, well, you don't have to, I'm going to rewrite it, but reflect back, I guess, to the previous page. We had probability of A and B is equal to the probability of A times the probability of B given that A has already occurred. All right. Now, like I've been mentioning throughout the whole course, coming up on, I wouldn't say the end of October, but we're moving into the end of October. So, end of the second month coming up. Haven't really done much algebra, right? Minimal algebra. Computation, yes. But even computation, we tried to let the calculator do the lion's share of that, right? Here's some algebra for you. I want to solve for a probability of B given A. I'm going to divide both sides by probability of A. When I do that on the right-hand side, the probability of A cancels out, and you're just left with the probability of B given A. On the left-hand side, we have a new formula. So this whole shibiggity bang here is that rule. So do you have to know that process, what I just did, the algebra? No. I just wanted to show you that to emphasize the fact that this is not really a new rule. It's just an adaptation of a rule we already know. All right. We worked with this rule on the previous pages. All right. So we're not really doing anything except looking at it from a different perspective. So now I want to solve for the conditional part of the multiplication rule. All right. That's all this is saying to me. So with that in mind, it should alleviate a little bit of the concern. Oh, here's another rule. You know, that's generally, when it comes to math and science, it's like another rule, another thing to memorize. You know, this is really not that. And in fact, we're even going to move further away from that idea by saying, let's just get at the spirit of the rule and use that to come up with a framework within the table that will allow us to make a determination of probability without actually having to rely on a rule every single time. All right, so understand the intent behind the rule, and then from there, everything will be fine. All right, so this is some real data from previous semesters. I actually just recently updated it because it was weird. I usually try to update it in preparation for a new semester, but I forgot this year for some reason. So I only updated it like 2 days ago. But this is up through, from fall to 2002 through spring 2018 in stat, just stat. That's the only classes that I compiled the data for. I only looked recently. Apparently, because what I would do is at the end of each semester, I'd create little tallies and keep track of all the A's, B pluses, and everything, and I put it in my spreadsheet. I didn't know the college was doing that for me. It sucks when I do all the extra work for no reason. So they have all of the semesters that I've taught since the beginning, all the students from each semester, and all the grades that each student has earned within the semester. And it is crazy. When I look back to like 2005, for example, and I look at the names in the rosters, and I'm like, wow, I don't recognize a single one of these names. That sucks. Yeah, it's crazy. But, 2005, it doesn't seem like that would be that long ago. It's like 15 years ago. It's crazy. So it's just time, man. It's time. It's insane. But anyway, I updated the data set, and I can show you that later. Just in case, just in case. I know you're curious. Why wouldn't you be? This is real data. How did the students that came before you perform? Well, at first glance, it looks like the females did a lot better than the males for the A's. So sorry, guys. You're out of luck. I think you're getting an A. Nah, if you look at the quantity, look at the total number of males versus females, you would expect a little bit of disparity, right? Because we're looking at 60 to 70 more females overall enrolled, right? So could that be the difference in the A's? Because it looks like the B pluses are pretty level, the C plus, there's a disparity in B's, right? The C's are pretty close, the D's, okay, the females are outgunning the males in D's. The males seem to be running away with the F's. Honestly, that has nothing to do, I don't think, with instruction as much as it has to do with perseverance. I've just noticed over the years, and this is only my own perception, and I feel like I've made all the general statements that I can in class, like after a test. Just keep staying with it, keep practicing, do what you need to do. If you haven't been practicing, well, you may want to try doing, all that stuff. I make all the general statements. Some people absorb those statements, some people don't. But I have found that when things aren't going right, like you get a bad test grade back or something like that, I find that the females are the ones that are coming up to the front desk and saying, all right, paid a lot of money for this class. How are we going to fix this? The males are more likely to say, all right, we'll get them next time. And that's it. You know, like if there's a gender that's more likely to pull a disappearing act towards the end of the semester, historically it's ended up being the males. Like they just stop coming. They're like, well, didn't work out this time, so I'm just not going to go. Saturday morning, you know. Friday night, Saturday morning. I'm just not, like, I got other things I can do. You know, the females historically, now I don't want to generalize about all females. I can't imagine that this is a microcosm of the entire human population and condition, but at least as it applies to my students, on generally Saturday mornings, that's when I usually have my stat classes. It's usually the females that are like, listen, come this far, paid the money. This is my last math class, dude. You're the only thing standing in the way. What are you going to do for me? You know, and if the student is doing any near, like, remotely near the coursework that's required for the class, it works out in the end. The only ones that end up in that true F category are the ones that are like, what are you going to do for me, man? And I'm like, well, I can't do anything because you missed every test and you haven't turned in an assignment. Oh, okay, when can I make all the tests up? I'm like, it's January, so you can't. And so that's it, you know, like that's the end of it. You know, these are the not going to do anything, but you're going to give me a passing grade anyway. Those are those people. All right, so that's a different story. I find that the males are just like, bombed a couple of tests, I'll get them next semester. You know, so generally it tends to work out. So some of those would-be Fs crawled up into the D categories. And basically everybody ends up moving up a level because it's like, well, I really need an A. So, or I really need a B. So maybe some of those would-be C pluses crawled into the B category because they figured it out, like towards the end of the semester. All right, what do I need to do? All right, it's coming down to the end of the line. It's the home stretch. Give me the recipe. All right, I'll do anything you ask. And we're like, all right, well, you got to study this. You got to come and get some extra help on this day. You have to practice these problems. All right, I'm going to do it. And then they do it, and then it all works out. All right. So part of this is a discussion of the data table itself, and part of it is kind of like a motivational speech if you're struggling. So this is always a good lesson in that capacity. Right? But there's a lot to be learned from this because you might look at it and, you know, you might have heard wah, 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 wah. Every word that I said after females get more A's than males in this class might have gone out the window. Because if you're a female, you'd be like, all right, lock it in, baby, I'm getting an A. If you're a male, you might have been like, all right, I'm screwed. You know, and then you might not have heard a single word after that. So let's dive into the probabilities and see how this plays out. So the first one is the probability of passing given that you're a female. All right? So the notation is saying that it's a given fact that you're a female. Now, you could go by the formula. I'll show you the formula this one time, and then I'll show you how you don't need to use the formula at all. All right? So let me just recall the formula. It's A and B over the probability of A, but in this format. So we identify the B value and the A value. So pass is the B value, female is the A value, and then we expand the formula based on that information. All right? So here's B, here's A. So we're looking at probability of A and B over the probability of A. So probability that you're going to be a female and pass. And then we would divide that by the probability of being a female. Now, this is a single individual, single event. All right, so we're not using the multiplication rule to evaluate the and. All right, because I'm not selecting two individuals separately. I'm looking for one individual that exhibits the characteristics of being a female and passing. All right, so I'm looking for all these females. Single event. All right, so you would add all these up. All right, because those are the cases where you're a female and you have a passing grade. So if you add them all up, now you can kind of use a little common sense, a little mathematical wizardry. In order to be a passer, you're not going to be one of the ones that failed, right? So if I just take the total number of females and knock off the 35 that failed, then these values must add up to that difference. So you can get the 304 that way. So 304 out of 609.
Where'd you get the 304 again?
I took 339. Well, the simpler way to do it is just to say that I added up all these values. But the other way to do it is to say that I have 339 people overall minus the 35. Now the probability of getting a female in general, well, there's 339 females. Overall, and there's 609 people in total. So 339 over 609. Now you could simplify that. And again, you don't have to simplify it like to lowest terms, but simplify it so it's a single fraction, 304 over 339. So that's going to lead us to our shortcut. And like I alluded to before, more than alluded to, I just flat out said it. We can use a formula without using the formula. Okay? As long as you know what the words mean. It's saying it's a given fact that we're dealing only with the females. So what I'm going to do is just highlight the relevant part of the table, the female column. So whatever the given is, that's the part that's relevant within the table. So in the case of the second example, which I'll get to in a second, the given is the male. So I would highlight the male column. Flag it in whatever way makes sense to you, because I know we don't all have highlighters. All right. Once you do that, you ignore the rest of the table and just find the probability within the highlighted area. So now I just want the probability of getting a passing grade in the highlighted area. So with that, I could jump right to the 304 out of 339 because I have a total. I don't know why I walked over there. I have a total of 339, so that's my bottom number. And the number of people that passed would be the sum of these values for everything except for the 35. So 304 individuals out of the 339 available passed. Okay. So let me contrast that with the amount of work that would be required for number 2 if you use the shortcut, which just involves some way of pointing out in your own mind what the given part is. So bring a highlighter to the test. Bring a crayon if you want. I don't know, like something, you know. Bring two colors, pencil and pen. All right. So we're looking only at the males. I want the probability that an individual fails. So here's my flunkies. There are 57 of them. Out of the total, which is 270. All right, so comparison of the amount of work. Same? No. In terms of the tables, yeah. I ultimately marked up the tables the same way. But for this, if I use the formula, I had to do a little bit more. I had to do a lot more. I had to conceptualize, I had to plug in probabilities for each component, I had to remember a fact. But here, it's just a matter of saying, okay, what's my given? Males, okay, forget everything else. Probability of failing, that's these folks, 57 of them. The total in this, only this category, is going to be 270. All right. And you can develop a little bit of muscle memory on this to the point where you start looking forward to these kind of questions. All right, because on the next page, you know, it's a little, there's a little bit more to it, but just the first part of this question, for example, probability of getting an A given that you're a male. So I'm going to highlight the males. All right, so the males. We have 270 of them. All right, same data set, so same total. The probability of getting an A. So the number of A students within that category only, 83 of them. As opposed to the probability of being a male given that you got an A. So I'm going to focus on this category, the A category. So I'm ignoring everything except for what I highlighted in green. Total, 228. The number of males within that category is still 83. All right. Now you can put these two fractions in your calculator, but if you take a number and divide it by two different numbers, you're going to get two different outcomes. So maybe you don't need to put it in the calculator in order to realize that they're not going to be equal to one another. All right. So my justification is this. So no, because of everything I just wrote. All right, and what that tells us, now it's not always relevant, but when it is, it's important. It tells us that the order does matter when you have particular events. Right? So if I'm looking at the number of A students within the category of males versus if I were looking at all of the males within the category of A students, I should not expect necessarily to always end up with the same proportion, the same probability or percentage. Right? Now, number 4 is a very important concept. I've got to put a different kind of star on that because stars usually mean homework. Let me do the creative star. That kind of star. This one's really important because it talks about the idea of proving independence for a particular situation. So we know things like dice, coins, and stuff like that. They're going to be independent because if I flip a coin twice, 3,000 times, or anything in between, There's still going to be two sides to the coin. Right? Whether I flip it once, twice, three times, four times, whatever, it's not going to impact whether I'm able to get heads or tails. There's always going to be one head, one tail, two sides. Right? Same thing with dice. There's always going to be six sides. Right? But that doesn't always apply in real life. Right? Sometimes a condition will impact the probability of an event occurring. So this question is really important, not only mathematically, but also you might consider academically, socially, a bunch of different possibilities, because you're looking at just a scenario, using that information, attempt to show that being male and getting a B plus are independent events. All right. So in theory, your grade and your gender should be independent of one another. One should not be dependent on the other. All right. If I walked up to a random person out in the hallway, not a stat student, and I said, "Listen, should your grade be dependent on your gender?" Pretty easy answer, right? All right. So the other way around, I think, is pretty obvious. Should your gender be dependent on your grade? That doesn't even make sense, right? Because it's like, all right, well, I'm a B student, so I guess I could be a male now. Like that's not how it plays out, you know. Like life doesn't work that way. You gotta. I mean, I don't even know what that would imply socially. Like you have to earn your gender. That sounds so politically inappropriate that I don't even want to continue that thought. But the other way around is like a concern, right? Like you don't want to go into a class or the workplace and say that your situation is dependent on your gender. I mean, my wife comes home all the time. This person's making more money than me. This person has the same job title as me and is making more money than me. I have more experience than this person who has the same job title as me and is making more money than me. I have more experience than this person, the same job title, and I'm doing more work than this person who is making more money than me. I have more experience than this person who is making more money than me, who has the same job title, that I am doing more work than, who is also a male. All right, so yeah, now you see it, right? It's pretty obvious. Like, what are some other things that might be coming into play? Tell me when you figure it out, because it looks like you got everything going for this individual. This person's not doing anything, getting more money, and it stinks to high heaven. It seems like it's only solely based on gender. All right, I'm in a profession where it's not allowed. We're paid on a scale. We're paid on, you teach this number of years, you have this many credits beyond your master's degree, this is what you get paid. There's no negotiation. It's not legal. Like, you cannot go into a school district and negotiate your salary if it's a unified school district, right? So it's just not, if it's a public school district, you can't do it. It's just not how it works, right? But in the corporate world, that is the definition of how it works, right? So we'll stay focused on the classroom because that's less depressing, right? So here we're talking about male and getting a B plus, but how about female and getting an A, male getting an A in this case? You know, I might be concerned about that. Is he unfairly giving the females A's and treating the males poorly? Like, what's going on here? The data is going to begin the discussion, but classroom observation, you know, just the overall atmosphere within the classroom, how I'm grading assessments, whether the assessments are balanced and fair. Those are all other criteria that go into a reason why these things might play out the way they do. Accessibility, you know, I'd like to think that the world is kind of evolving past certain things, but then you read in the papers that it has not. So, you know, everything kind of comes into play. But the data analysis, you can't say that there's bias because the data is saying that there's bias, but you can say that there is enough room to pursue that avenue based on what the data is saying. All right. So here's an example. So what we do is we're going to take a look at, now the structure is probability of B given A is equal to probability of B. So let's look at the one that makes sense, because again, probability of being a male given that you got a B plus, or probability of getting a B plus given that you're a male. I like that one better. All right, because that one is dependent on the gender. Now, you might make a case for other types of situations for the reverse, but again, the idea is that you don't get to be a male because you got a B plus, right? But there are some situations where, hey, you're part of the boys club, so don't worry about it. Just give me a 6-pack, I'll get you that. You know, like, is that how it's gonna be? You know, is it fair? Or is it a fair class to be in? We want to know that. All right, so if it's fair, well, in this one case, getting a B plus, then this should be the same as, or roughly the same, because life is not exactly equal. These are data points. Now, something you got to understand is what we talked about the first day of probability, which I think was last week. The law of large numbers. As you increase the number of trials, you're going to get closer and closer to the true probability distribution. So I can tell you that as I continuously update this data, these two numbers that we're going to get, they started off far apart. As the years have gone on, they've gotten closer and closer together, and now I feel compelled to go back and actually get all those data sets from like after 5 years, after 10 years, after, and so on, and show how those numbers have come together. But that's a me thing, just out of curiosity. But this is what we're looking for, because if they're independent events, these two should be roughly equal to one another. Because statistics, it's not always going to be perfectly equal, but roughly equal is good enough. All right, so left-hand side, the condition is that we're looking only at the males. So I got 56 of them over 270. All right, 56 B pluses added to 270 males. Now I'm just looking for B pluses in general. So I grab all my B pluses and the grand total. Now remember before I said unsimplified fraction form is fine, but sometimes for your own purposes, just to get a sense of the situation, you may want to pop it in the calculator. I think this is one of those situations. 56 out of 270. Mm-hmm. I have no idea what that's going to be as a percent. Mm-hmm. I can't even conceptualize. We're looking at about 21%. All right. 114 out of 609. About 19%. All right. So we're in the neighborhood. All right. Are we there yet? No. Are we ever going to be there? You wouldn't know that because I didn't show you the data as of like 10 years, as of 5 years, and so on. So you just have to take my word for the fact that these numbers are moving closer together. But for now, we would say that they're not independent because 0.21 is not equal to 0.19. But I can promise you that it's a lot closer than the after 5 years when it was 0.28 and 0.12. You know what I'm saying? It's moving closer. So if I teach for another 10 years, and another 10 years, and another 10, oh geez, that's depressing. If I teach for another year, and then another year, and then another year, and then maybe 5 more years after that, and then retire or something, with full benefits and a yacht, then that's much more pleasing. Then these numbers should be pretty close to one another. When all is said and done, it should come out in the wash that people look back and they say, He didn't discriminate. Didn't matter what your gender was. Didn't matter what your race was. Didn't matter what your hair color was. Didn't matter whether you had hair. Everybody was treated equally in his class. Sometimes too equally. I don't even know what that means. So, but yeah, that's the idea. But now you have a skill. Look at that. You can take this right out of the classroom today, and you can think about your own life. Have you been treated unfairly? We all have, in some capacity. But is it worth collecting the data over? Right? Because I know that my sister ducked out of doing the dishes when we were kids more times than she was supposed to. Okay? It was always my day to do the dishes. I'm not collecting a data set on that. All right? But I know it in my gut. Like it can't be my day again. I just did it yesterday. So there's those situations, but then there's situations where it's like, yeah, you want to pull this stuff? Now I'm going to start collecting data. All right? Because I learned how to do it, and now you're screwed, pal.
It wasn't about data, but she's bullying you.
Yeah, well, she was younger than me too, so that's like, yeah. It was psychological bullying because it was like, it always started with, it's your day to do the dishes. I'm like, it can't be. I just did it yesterday. No, it really is. I'm like, listen, you're pulling a fast one, and I don't like it. Mom, he's being mean to me again. I'm like, all right, fine, I'll do it. So I had it all figured out. I fell for it every single time. All right, so you have a skill. You can take this, collect your own data, and now you have a way of making a determination of whether a situation is fair. Now, sometimes you want to know what the situation would amount to if there were no bias involved whatsoever. All right? So we're going to learn, and this will be the last thing we're going to do today. We're going to learn about some simulations. And they're fairly easy, only because it's the same process in the calculator every time. But it is a process in the calculator. So you know what that means. There's steps. And so you got to know the steps. Right? The other option would be on a test actually rolling a die 300 times, physically. One student thought he was being funny during a test about 10 years ago. Brought in a die during a test. Started rolling it. You know what a die sounds like when it's being rolled on one of these tests? Once or twice, it's annoying. Well, actually, the first time it's funny. Second time, all right, we get the joke. Third time, now it's getting a little annoying. 50th time, you gonna do this the whole time, pal? Everybody else is doing their simulations on the calculator, and this kid is rolling a die over and over and over again. Now, it was my fault because I thought it was a joke. I was like, or you could just roll a die 300 times. So the kid took me up on it, and yeah, 300 rolls later on a test. Yeah, that sucked.
So no dies.
No, I please do not bring a die to the end of the test. I was going to make a joke and say, unless it's one of those fuzzy dice, that doesn't make any, but I could see somebody doing that just to be a jokester. So anyway, the calculator is going to do the job for us, and it's also going to do the calculations for us, so why not? Right? So we'll focus on the dice. Coins, you'll understand how to do coins once we handle dice, and actually, once we handle the examples that I go over here, you'll know how to do everything because it's the same process in the calculator. So the simulation, it's just 7 rolls of a fair die. You might look at that and say, well, 7 rolls, that's not too bad. I actually could do that by hand. But we don't want to do it by hand because, again, the law of large numbers is going to take hold at some point. And again, the law of large numbers is just stating that as I increase my number of trials, I'm going to get closer and closer to the actual probability. Right? Now, I know what the probability of getting a 4 is when I roll a die. It's 1 out of 6. All right? There's one side that has 4 dots on it, and there's 6 sides overall. What I'm using the simulation to do is to verify the law of large numbers, to really make sure that I have a technique that's going to work when I expand beyond dice. All right? So I have the steps listed out here. Probably a little too vague, so I'll take it as a typo to be a little bit more specific with the steps. The math probability, that's easy enough, but random integer, I believe, is option 5. So it's a little confusing here because I wrote it as steps 1, 2, 3, 4, and 5, but people in the past have looked at this and they're looking for like option 3 to say random integer, but this is option 5. Damn it, wrong thing. All right. Also, this sideways arrow, that's the STO key. That's right above on. STO with the sideways arrow. It's the store key. Store, the key that stores. I've had people be like, what's a store key? I'm like, I don't know. So, well, I want to run a simulation. We're going to do math. So math is right here under alpha. We're going to go over to probability. All right, so that's, see that's already the first like weird step. So maybe, oh, you're just hitting math. Yeah, there's just math key, brings you right here. So if you're confused by this, what I would say is get rid of the numbers that are in front of each of the steps, because people are looking to hit the number 2 to find probability, and that's not how you do it. So, and I'll take that as a typo. So you were in the home screen, you just hit math, you're going over to probability. So you could hit the left arrow once to do that, or you could hit the right arrow 3 times. Either way, it's left or right arrow to get to the probability menu. And you'll see an option for rand int. So that's option 5. So hit enter on that. Then you're going to type in these values, and I'll explain what they mean in a sec, but just type them in for now. So 1, comma, 6, comma, 7. The comma, again, right above the 7, it's its own key. People spend a long time hunting around looking for the comma key when it's hidden in plain sight. They're like, what alpha do I have? Alpha what? Second what? No, it's its own key. And then after that, we're not going to close parentheses. For whatever reason, that causes a break in the function. Sometimes, not all the time. So after that, you're going to hit the STO key, store. Why I can't just say store, I don't know. But it brings up a sideways arrow. And then you're going to type L1, so second one. Right? So the same L1 that we've been using all course. Right, so that's nothing new. And once you do that, hit enter. And you're going to get a display of values. Now, before anybody says, wait a minute, I got different numbers from you, and then follow that up with somebody else saying, wait a minute, I got the exact same numbers as you. There is the term rand. That rand represents random. All right? So if you got different numbers from me, you should have. If you got the same numbers as me, that's okay too. Hit the STO key, which is right above on. All right? Because what the calculator is actually doing is it is randomly selecting numbers between 1 and 6. and doing it 7 times. All right? So it's the same idea as rolling a die 7 times. All right? But it's giving you all the outcomes in one shot. All right? It also is storing it into L1. The reason that's beneficial, we don't need it right now, but we want to get in the habit of doing it, is because if I want to sort out the information or find a mean or a standard deviation, I don't want to have to write all these numbers down to then type it into a list to find the mean and standard deviation. Let the calculator do the work for you, right? So random integer 1, 6, 7, L1 is going to give me a random set of values between 1 and 6, 7 times. So roll the die the first time you get a 6, the second time you get a 6, the third time you get a 1, and so on. All right. Now on your calculator, so random integer functions, if we all bought calculators, brand new calculators today, turned them on, unboxed them, turned them on for the first time today, and use this random integer function, we'd all get the same random integers. All right. And that's because these numbers are random to us, but they're based on the formula that the calculator uses to generate random numbers. They all have the same formula built in. The more times you use the random integer function independent from me in class, the more you're going to start deviating from my random numbers. All right. So if we all had brand new calculators and we did random integer function, the same integer function, like 10 times, we would get the same array of values 10 times. But if you did it 20 times and I only did it 10 times, then we would start to deviate every time we did it after that.
I'm gonna get syntax error.
Syntax error. Did you close the parentheses?
Should we stick something in L1?
No. I mean, it's going to get typed into L1, but
And close or
no close.
no?
You got it? Oh, you got the error? Oh, okay, yeah, you actually do put the L1. And then when you do that. Oh, you see, you get the same values, right? Oh, you have a different display. So it's the same numbers, just you're going to put the 1, the 6, and the 7 here.
What's the 7 for? Because it's only 600. 7 rolls.
7 rolls. All right, so let me see if I could change the display on my calculator so that for those of us who have a different model. It's so tiny that I can't see. All right, so let me do it this way. So if you have a different model calculator, it might have come up like this, in which case you're going to type in 1, 6, and 7, and then you're going to go to paste. So this is for the newer calculators. Well, actually, I don't even know what's new anymore. There are, like, you could still buy the older models as new calculators, so it is what it is. The problem is it won't automatically store it, so then you have to do what we did once you get here and hit, like, replace that close parentheses by hitting store and then second one. And then it'll do the same thing again. All right, but you could see I used a brand new calculator. You see how it gave the same distribution of values? All right, that's going to happen. All right, but when I do it a second time, so I'll just run this calculation a second time. Unique set of values. So do it a few more times. You can see that every time it's jumbling it up, giving you a fresh set of values. All right. So don't always expect your numbers to be the same as mine, but if they are, don't be alarmed by that either. All right. So the probability of getting a 4 in this case, well, there's a 4. I got 1 out of 7. Now this is an experimental probability. experimental probability. All right, this is important to realize because, again, we already know what the probability of getting a 4 is. It's 1 out of 6. This is saying 1 out of 7. So it's clearly wrong. Well, it's not really wrong. This is what happened when you walked into a situation. I mean, there's got to be an age. I don't know what the age is, where a kid is familiar enough with numbers to be able to roll dice and write down the numbers, but not familiar enough to think about things like probabilities, like what are my chances of success. So that age kid, you'd have them roll the dice. Roll it 7 times. How many 4s did you get? Okay, now roll it 100 times. How many 4s did you get? Roll it 1,000 times. How many 4s did you get? For the lower number of trials, you're not going to get always a number that's very close to the correct answer. But as you get to the higher number of trials, like you have 25 kids in a class, each one is doing it 7 times, compile all their data together, you put it all together, now you're talking about 175 trials as opposed to the 7 trials. You're going to get a probability that's going to be pretty close to the true probability. All right? Wouldn't necessarily be exact still, but it's going to be closer, consistently closer. All right? So the next one is 300 rolls of fair die.
Professor, why do we then go to start and edit? Like that brings us to like the column table. Why do we do that?
Why? Oh, stat and edit would bring you to the column table if you wanted to do some other calculations with it.
So we don't.
In this case, you don't need to do it. We're going to do it in the next case. All right. So let's do it again. Math, probability, option 5. And again, it's still the same parameters, but this time you want to store it. I'm sorry, not 7. This time 300. This time we definitely want to store it in L1. Before it was kind of like a luxury to build up muscle memory. Now it's like we gotta do it.
Set math, probability, option 5.
Yeah, it's the same process. The same as the last one, except we're putting 300 in instead of the 7. All right, and so then you hit enter here. And it takes a couple of seconds because the calculator is running through its program to figure out these random numbers. Now you can see that this will get out of hand pretty quickly. All right, the 7 outcomes, I chose 7 for example 1 because for the older calculators anyway, 7 was the most values that you could fit on the screen without having to scroll. Here, you see the right arrow tells me that if I hit the right arrow on my calculator, I can start seeing more values. But then eventually it starts getting difficult to keep track of the transition from one screen to another. So that's where we want to go into the stat editor. Stat edit. And now you can see all those values are stored into L1. So you're hitting stat and then edit. Stat, this one, the red one. All right, so now we have all these values here, and you could, I mean, there's 300 total, so that would suck, but you could go through and, oh, there's a 4. Keep going. There's another 4 coming. Oh, there it is. There's a second 4, and then eventually you'll get them all. But you're not interested in doing that, I don't think. So let's try something else. All right. So let's quit out of here. So it's second mode. Go back into your home screen. This is the technique that we want to use. We want to sort it out. So we're going to look at the sort function, which is in the stat menu. All All right, so hit stat. It's option 2, sort A. Oh, I'm just writing the function again. Stat 2 is what I wanted to write. All right, so in your home screen, that's what we're going to put in. We're going to sort ascending, so option 2, and we're going to sort L1, so second one. And after all that, all it's going to do is say done. You'd be like, done with what? So sort ascending L1, and then it says done. You're like, oh, cool, great, wonderful work. What did that accomplish? Well, what it accomplished was it sorted L1 in ascending order. Ascending order just means going from smallest to biggest. So now when I go back into my stat editor, all the numbers are going to be in order. It's going to be easier to count. So stat edit. Now I can see all my ones are in order. Now, I mean, it's still annoying, but because I need the probability of getting 4s. There's a little workaround here, but it's not for everyone. So if you figure it out, you could definitely use it. But the technique I'm going to use is the one that's printed, and that is I'm going to find the first 4. Because I still don't really want to count up the values. So if you hold down the down arrow, it'll scroll for you a little bit faster. It's just I can't do that on my screen, so I got to do it a different way. So I'm just hitting alpha down. Alpha, if you hit alpha up or alpha down, it'll skip values along the way. It'll go by 7s, I think. Well, in this calculator, I think it's by 10s. Yeah. So alpha up and alpha down goes every 10 values from where you were previously. It's kind of like the conveyor at the airport. So you might overshoot the number, but you'll just walk back a little bit. Alpha and then the down key, and then it skips a few along the way. But I overshot it, so what I need to do is go back, and then I'll have it. So the first instance of getting a 4 I've identified as the 159th value. All right, so, and this is all optional, the strategy I'm showing you, but it's optional so that you could avoid having to count up, okay, I got 1, 2, 3, because if there's like 47 values, it's very easy to accidentally write down 46 values on a test. So this is the position. So it's the 159th value is the first 4. All right, so then what I do is I go back in. I'm going to, again, alpha down for me. You can just hold the down arrow down if you want. I'm just looking for the first 5 now.
And ours could be different based upon like if we ran it once or twice.
Exactly. Now we are doing 300 trials, so whatever our percentage is, it should all be in the same neighborhood of each other, but we should be looking at relatively different values. Again, like as you said, if we did it a differing number of times, the random integer function. Let me just make this roughly the same size. All right, so this is the position, the 204th value. All right, so what I do is I subtract those positions. So 204 minus 159 is going to be what, 44? 45, yeah. 45. And there are a total of 300 values. All right, so that's what we got as our experimental probability for rolling a 4. I mean, we've gotten the answer, but I'd like to know what that looks like. About 0.15. Well, it's exactly 0.15. But how does that compare with the true probability, I wonder? So 0.15 is the probability of getting a 4 using an experimental approach. So abbreviate experimental EXP if you want. You can write it out. 1 out of 6 is what we should have gotten, which is 0.167 roughly. When we did it only 7 times, I got 1 out of 7, which is about 0.143. All right, so we got closer. We didn't get a lot closer, but we got closer. All right, so when I did it with only 7 trials, I got about 0.143. When I did it 300 times, I got about 0.15. I should have gotten about 0.167. All right, so it's moving towards the correct probability. It doesn't matter how fast it moves towards the correct probability. It's just got to move towards the correct probability. All right, so if you follow this line of reasoning, you could say, all right, well, I didn't have to roll a die 300 times, so that's my first win. It took a couple of seconds to do it, but what if I rolled the die 900 times? What if I rolled it 10,000 times? You know, what would I get as my probability? You can probably be reasonably assured that it's going to be the 0.167 that you're rooting for. All right. Now the calculator does slow down when you increase the number of tries. For some reason, it slows down to a snail's pace in the sorting. The random integer function, it gets slower, but not noticeably like, man, is this going to take all day slower? The sorting function does get like that. Like if you did a random integer and ran it like, let's say 950 times, it would take a couple of seconds to do the integer, the randomization, but then it'll take like a minute and a half to do the sorting. And you're like, is this ever going to work? Now, if you go over to Excel or Google Sheets, it does it instantaneously. All right. So these skills, they do actually transfer over to Excel, so that if you really wanted to see, you know, like I want to do 20,000 trials, Excel can handle that easily. It'll do it instantaneously, and then you'll see that the probability will be. I mean, it may not be exactly this number. Maybe that'll be an 8 at the end. But it's going to be pretty spot on when you increase those number of trials to extremely large values. All right. And so you look at this and say, okay, cool. You showed us another calculator trick. Why would I need to know this? Well, we spend a lot of time talking about cards, dice, and coins. But the real world, outside of casinos, doesn't really deal much with cards, dice, and coins. All right. So how can I evaluate probabilities for situations that just don't have a formula? Like I look at it and I want to make a determination of whether my workplace is a fair environment, or whether I'm likely to get into a car crash at this freaking intersection over here because of a schmo is not going to obey the traffic signs. Okay? I mean, stop sign, no stop sign. It's pretty simple, but people screw it up every single day. All right. You could look at it and say, okay, well, there's 2 stop signs out of 3 possible places to stop. So my chances of surviving are 1 out of 3 or 2 out of 3. What's your justification for that? All right. No, what you got to do is you got to sit at that damn intersection and look to see how many people are blowing the stop sign. And then how many people are ignoring the fact that there is no stop sign and actually stopping there, all right? Because those are potentials for accidents, all right? Because an accident doesn't need to occur in order for there to be a potential for an accident to occur. So that's what we're looking at. So then you collect that data over the course of, pick a number of days, pick an hour of a day, and now what you have are experimental probabilities. You're creating the foundation of a simulation, all right? So let's say you do it for the course of a week, and you're only interested in Saturday mornings, maybe, all right? So you do it after class because you want to get out of here safely, or you do it coming into class because maybe you're coming in right at the buzzer and you want to make sure that you're not going to get killed because you're just trying to get to class on time. So, but you get here early and you sit out there with a lawn chair. You do it over the course of a couple of weeks, or maybe a month because it's only Saturdays. And you do it for like 20 minutes, half an hour. You collect that information. You have a percentage. Now you can create a simulation, and you don't have to sit out there with a lawn chair for the next year and a half. You can simulate what would happen if a year and a half were to play out on your calculator or computer, and then use that information to make a determination of whether or not that's a safe intersection. I mean, I don't know if it's safe or unsafe in terms of getting into an accident. It's unsafe for other drivers when I'm coming through, for the fact that at some point I'm going to lose my mind and get out of my car. That's really what it's coming down to. Because the next person that jumps that turn in front of me, I'm going to have a conversation with them. And it's going to get ugly. Because it's brutal. It's like I'm coming through and you can see the person nudging. They're nudging. I'm like, don't do it. And I'm saying, I'm driving in the car. I'm saying, don't do it, don't do it, don't do it, don't do it. I have my hand over the horn. Don't do it, don't do it. Then they start going, and then I'm on the horn, and then they're halfway into the intersection. I'm like, I'm not stopping. You are going to stop. I'm blaring the horn, and I'm driving past them, and then I'm giving them the old salute on the way out. You know, and that's just how it goes. But eventually, it's gonna get ugly. So it's something to keep in mind. You could apply this. You know, take the conditional probability and this concept, put it together, and now you have a skill that you could take right out of the classroom into the real world, right? So I'm going to put stars on these problems because these are the ones that I would like you to try on your own. One of them's pretty easy. The other one, we'll be talking about this one in detail next class, all right? And so that is where we're going to leave it today. So, okay.